Okay, in this presentation we're going to look at normal random variables. So everything in this question is to do with the normal distribution and normal random variables. Okay, so handcrafted widgets are made in two types, A and B. Now, all widgets require an initial process which takes a time x, which is distributed as normally distributed with a mean of 10 and a variance of 12. That is to say, a mean of 12 minutes and a variance of 12 minutes squared. Okay, so it's not a standard deviation of 12, it's a variance of 12 minutes squared. Type A widgets take a further random time, YA, to complete, which is distributed as a normally distributed variable, which is 15 minutes with a variance of 16 minutes squared. Whereas type B take a further time, YB, which is 12 minutes with a 9 minutes squared variance. Okay, now here x, YA and YB are normally distributed. Okay, so the first question is as follows. State the distribution of the total time to make type A widgets and type B widgets. Okay, so this is the crucial part of the question here. How do you combine normal random variables? Okay, so essentially what we have here, now this is not related to the question, these are just two generic expressions of two generic normal random variables, xa and xb. Mu a and mu b, and variance is sigma a squared and sigma b squared. Okay, so if you want to get the addition of those two random variables, which is xa plus xb, essentially what you do is add the means and add the variances. Similarly, if you actually had three random variables, you could just actually do it the same way, add up all the means, add up all the variances. Now, subtraction is also important here. So xa minus xb, what do we do? Well, we subtract the means, okay, mu a minus mu b, if we're talking about the variables xa minus xb. But watch out for this here, we still add the variances. So watch out for this big plus sign in the middle there, okay? You might be tempted to go by reflex almost, sigma squared a minus sigma squared b. No, it's a plus. Anyway, so just using that, let's have a look at our answers there. Essentially what we do there is a time to complete type A widget is the initial process x, which takes x minutes on average, and the special process for type A widget, which takes 15 minutes on average. Essentially what we do there is add the means and add the variances. So we have a mean of 25 minutes and a variance of 28 minutes. Likewise, for type B widgets, add the means, 10 plus 12, add the variances, 12 plus 9, and we get our expression for our combined variable, normal variable, which is a mean of 22 minutes and a variance of 21 minutes squared. Okay, I should correctly always say minutes squared when talking about the variances, but I might sort of slip of the tongue, just say minutes. Okay, so part B is as follows. Two particular widgets take the same time in the initial process. So the first process x is the same for both. So if one is of type A and the other is of type B, find the probability that type A widget is completed first. So essentially what we're doing is comparing the secondary processes for a type A widget and the type B widget, and checking if the probability of a type A widget being completed first. So if x is the same for both, which we are told here, we require YA to be less than YB, which is to say that the difference is less than 0. Now, I used the expression there previously. I discussed the expression there for subtraction or difference. There should always be a question where the subtraction, that expression for subtraction, the difference of two normal random variables will come in useful. It's always disguised here. So if you think about it and work backwards from where I am, you can sort of see that it actually would make sense. But, you know, if you read this question at the first instance, it might take you a while to realize that they're asking you about the difference between the variables. So anyway, the difference is the combination of these random variables, or the differences, is as follows. YA minus YB is normally distributed with a mean of 15 minus 12, which is 3, and a variance of 16 plus 9, which is 25, okay, square minutes, a standard deviation of 5 minutes. So essentially what we have to do is calculate this here. Okay, so I realize actually I'm not being consistent. Not that it actually matters for continuous random variables, but just for the sake of consistency, I'll make that less than. Ya minus yb less than 0 equals z score of less than 0.60. So this is the z score. Hopefully you should be familiar with z scores at this stage. Z score or Z measure. Here it is 0, which is the measurement, is the observation that we're assessing the probability of. The mean, mu, 3, all over the standard deviation, which is 5. And that is the square root of 25. Okay, little bit of a revision there on Z scores. So the Z score is minus 0.60, minus 3 over 5, minus 0.60. Now, that is the phi function there, and I'm going to start using the phi function a bit more often, and that is the cumulative distribution function of the standard normal distribution, okay? And you should be able to recognize one or both of these from tables. Also using that from something like R. So when you work it out, and I won't work it out in this question, I won't see where it comes from, I won't show where it comes from other than say it is minus 0.2743. Now, just to be clear, if you're doing this by hand or pen and paper or tables, this is the symmetry rule. Symmetry, my pen is not working very well. That's the symmetry rule, using the symmetry rule there, in case you need a little bit of an extra hint as to how that came about. Okay, 1 minus phi of 0.60 should give you 1 minus 0.7257, and that should give you an answer of 0.2743. So that is the answer there. That's what we're looking for. 27%, or approximately 0.2743. So the next question is as follows. Find the probability that a randomly chosen type A widget has a shorter total completion time, than a randomly chosen type B widget. So this question is very similar to what we've just done previously, but what we're doing is considering both the primary process and the secondary process, X and YA and YB. So what we're going to do here is write the total time for both variables as WA and WB. And again, the logic of the question works out the same way as we've done previously. So essentially what we want to do is find the probability of WA being less than WB, okay, which again we can express this as a difference and use this formula here. So this is using our results from part A. The 25 and 28 is the mean and variance, the total mean and variance of type A widget. 22 and 21 is the total mean and variance of a type B widget. So 25 minus 22 is 3, and 28 plus 21 is 49. Okay, so the difference is normally distributed with a mean of plus 3 minutes and a variance of 49 minutes squared. So we're doing this the exact same way. So I'm going to skip through this very quickly there. And here I've actually wrote out the Z score in more detail. So, and again, let's just be, for the sake of consistency, we'll make it less than. And again, less than or equal to, it doesn't really matter a whole lot with continuous random variables. So we should get a Z score of minus 0.4285, and depending on how close you want to be with that with tables, should be fairly close to minus 0.43. So you should get an answer very close to this if you're looking at tables. We're using the symmetry rule again. So the phi function of minus 0.4285 gives us something close to 0.3341. In fact, it gives it exactly that value if you're using this number here. But if you're using statistical tables and you can have to work with 2 decimal places, you should get an answer close to that. Okay, 1 minus 66% or something like that should give you something close to 0.3341. So anyway, that is our answer there. 0.3341, 33% approximately, 1/3. Okay, the next part. Widgets of each type are packed in boxes of 16. Find the probability that the sample mean completion time a box of type A widgets is less than a box of type B widgets. Now this is using the normal, the sampling distribution. So the average time is the average of averages here, which would be the expected average there would just be the means in both cases. So 25 and 22, okay? Now, this is the sampling distribution of the sampling mean. Now, this is where things are different. We're looking at the variances now. So what we do here with the variances, and when we're looking for the variance of the sampling distribution of the mean, what we do is get the variance of the underlying distribution and divide that by the sample size. Okay, so here we have a sample size of 16. So variance of x divided by n, and that is the variance of x bar. So sampling distributions. So essentially what we have to do is essentially use all the numbers we used previously and divide by 16. So let u be the difference in the means of the two boxes. And so it's normally distributed with a mean of 3 and a variance of 49 over 16. And require that u is less than 0, that is to say the type A box is completed first. So moving down, I just paused it there for a second. Move it down. Probability of u less than or equal to 0 is the z-score of, and again probably should keep that consistent, minus 1.7143, or as close as you can get to that with your tables. And so therefore the phi function is minus 1.7143, which gives us a probability of 0.0432. So just to check where the z-score came from, it is 0 minus 3, which is the mean. Whoops, let's undo that. And 7 over 4. 7 over 4 is the square root of 49 over 16. So just working that out, algebraically, that turns into minus 12 over 7, which is minus 1.7143. Again, if you're using tables in an exam situation, that you use 1.71 or minus 1.71 or minus 1.72, and you should get an answer reasonably close to this. Okay, we'll leave it there.